so much for inviting me to give this talk, and it's great to have this sort of connection with the chemistry teachers rather than just being university, get on with things, and then chemistry with all the curriculum and teaching. So I'm very grateful for this opportunity, and if I will put my contact details right at the end, but if there's anything that we can do in solid state, then please get in touch. So as Jill kindly mentioned, I'm Lizzie Driscoll, so I'm a PhD student in Professor Peter Slater Group. I'm a final year, so we're nearly there. And my talk is about lithium-ion batteries. So born in the 90s and we're still fussing about them. So why? So because I knew it was going to be a chemistry teachers meeting, instead of going full on hardcore solid state, I decided to introduce myself. I'm going to introduce myself a bit more about the career sort of things you can pass on to teachers and pass on to your students about the sort of paths they can go down. Introduce obviously lithium-ion batteries and some of our research that is currently going on. And we've been quite active in our outreach, so I'm going to mention some of the resources that we have on hand for you guys as well. So without further ado, so who am I? So I know, and I have a look on the WMCTC programme, there's a sort of a lot of familiar faces on there, and probably we met a few of you earlier at that RSC top of the bench, but I'm probably just a nobody PhD, so I thought let's say hello properly. So any students who are thinking of going down my career path, I did do maths, chemistry and physics A-levels back in 2013. And I did my undergraduate chemistry industrial experience at the University of Birmingham. So my interesting play was at a solar company startup, so you can see me looking fresh-faced there right in the left in the lab coat. And given the talk, I was also funded by the Royal Society of Chemistry, so I had the opportunity to go down to Burlington House. Graduated in 2017 and I decided to do a PhD with Pete Slater. And this is quite a fun graduation photo, second from the right, and just an example of me teaching the undergraduates. So, I am a solid state chemist. I am in the energy materials sort of theme, and I just kind of want to point this out because I am quite passionate about trying to get more of us knowing about solid state and having more students know actually chemistry isn't just about drug discovery and pharmaceuticals. So that's why I just asked earlier about, or like if you had a preference for organic, and hopefully might convince you that solid state is cool and fun. And for those who already kind of like this side of chemistry and fab, and hopefully there'll be something that can help with the engagement with students. And I just think sometimes, yeah, as I said, chemistry, it's sort of, with the sort of solid state, we're kind of overlooked in what we can do. And I know in the UK curriculum, definitely the A-level, the only thing that's mentioned on batteries is just after electrochemical potential and just says lithium cobalt oxide with the redox. So I'm really passionate about the technology that everyone's got to hand. Students probably tell students off for handling their phone in class that they've got this technology, but we could explain the chemistry to. So this as well with smartphones, laptops, I've got two on my desk, and it's a Nobel Prize winning discovery. So great win for 2019, awarded to Goodenough, Whittingham and Yoshino. So this is just sort of the background of like, well, born in the 90s, and I chose the title just to try and, relate to myself as well. So it's 30 years on, and it only just got a Nobel Prize, but take this as an amazing win for solid state chemistry. The difficult thing probably about solid state chemistry is we are on the borderline between chemistry and physics, so a little bit icky. But these batteries are literally everywhere, and you can see in the past 10 years how it's revolutionised social infrastructure and the communication. And maybe in like the past year, you might see that there's more electric vehicles and there's a greater interest for the swap from internal combustion engines. But I'm quite proud we've got a solid state win, and I just remember I was so like, it's amazing. So I know the Nobel Prize prizes will be released probably in the coming weeks in early October. So my talk overview. So enough about background, enough about me. Let's get cracking. So I'm going to introduce the chemistry behind it, and oil rig I put here is your friend. So I know a lot of students struggle with electrochemical potentials and think it's nasty, probably think it's physics, but really it's really straightforward to get your head around it. And once you know one thing, it's fine. I mean, I'm going to say that obviously I'm biased to solid state. I'm going to talk a bit more about how they operate, and we've got a cool sort of demonstration and the videos online to help you support this as well. I think it's also quite nice, rather than just having the sort of curriculum where students learn it, it's quite nice to have the sort of applications. And again, we worked with their students as young as 8. It's as simple as like, well, they know how these batteries work just by simply saying, well, what do you do when you run out of charge, you can't play your games? So think about plugging. So it's getting those sort of ideas, they've already got them in their head, but it's sort of relating to actually, you kind of know a lot about chemistry already. And then the final part of my talk is, it's going to be what's all the fuss. So we're going to look into current research efforts. I'm going to touch on things, some things might, I know they feature in undergrad, but I think it's quite nice to mention it too. And I'll also finally finish with resources just to help chemistry teachers out too. Well, you guys, sorry, talking third person. Okay, so redox. So I've made this graphic here. So we've got the oil rig, oxidation and reduction. And it just kind of shows you need both. They need to work as a pair. You can't have an electron going rogue. So you've got to have the oxidation to provide the electron. But then also you've got the reduction to take it. So this is just, I related it to what I believe is also in the UK curriculum when it mentions lithium cobalt oxide. So this is on discharge. So your lithium metal will be giving up the electron, you get a lithium ion, and that electron wants to go somewhere. So it's going to go to your cobalt, and then it's going to reduce it. So they work in pairs, and just understanding this principle of redox is essential, and that's all it is to these batteries. And obviously you go a bit more complicated when you look at your reduction tables and you find out what's favourable. But this is all it is. So once they've got the half equations, you're away. So that's why I just want to reiterate that. So I know this diagram looks incredibly a bit crazy, but I thought if you have my slides at some point, you can maybe look over it, and it does look a bit nasty, especially when you see cathode and anode, and we'll talk about rechargeable batteries. So just to talk an overview sort of how lithium-ion batteries work, and the sort of, I've gone for the archetypal structure. So we have two, well, any sort of battery, you've got two electrodes and it's separated by the electrolyte. So in the lithium-ion battery, you've got one that we know as the lithium transition metal oxide electrode. So you have the lithium cobalt oxide. And this is a layered structure. So the purple sort of blocks you can see, apologies. The purple layers, that represents the cobalt oxide, and the blue little spheres you can see on the diagram, that's our lithium ions. And on the other electrode, we've got another layered system. And I always talk to the students, well, where can we find graphite in the classroom? And earlier in the summer, we did an outreach event, and the Faraday Institution sent me some cool pencils where it said, what do I have in common with batteries? And obviously it's graphite, you can get it in pencils. So on charging, what's happening is the lithium is moving from the lithium cobalt oxide, and it's going into your graphite. So all the electrolyte light is therefore, is just to help the sort of shuffling motion. And in an external circuit, you'll also have the electron moving. So that also relates to what I just mentioned previously with the redox. You've got the positive and you've also got the negative. So on discharge, all that's happening is the reverse. So you can relate it to your delta G, sort of favourability. Because you're applying a current on charging, it's not too happy, it's not a favourable route. So on discharge, it wants to go back. And just to point out as well, so I've labelled it cathode and anode, and I know students get incredibly confused by this. I think it's just because electrolysis cells are taught before galvanic, and the definitions are opposite. I remember looking through the GCSE revision guide and then the A level, and it's the opposite. So I will try and avoid those terms, but just so you know, if I say cathode and anode, it's based on the discharge. So the cathode in this case is the positive electrode, and the anode in this is the negative. That's the thing about rechargeability. Even people at my level, PhD and beyond, I've seen at conferences they label them wrong, and I'm just like, oh. But anyway, just simple. The cathode, it's got the lithium to begin with before we start charging. Okay, so Jenga I mentioned. So what has Jenga got to do with any of this? So just like the Jenga game where you have the tower blocks, you've got different layers, we can relate to the structure that we just had before. And it quite nicely shows, we used to quite nicely show how these batteries work. So using the same sort of key as before, the only different things that I didn't really touch on is the current collectors, and they're just there for the electrons. So on the oxide electrode, you've got the aluminium, and on the graphite, you've got the orange. And you can see I'm just ignoring the electrolyte because it's not important in this part anyway. And so what we can use with this set is, all these videos are available online, by the way, and I did put the little QR code for the paper if you want to see it there too. And again, what I just said about with the sort of charging, discharging, on charging, what's happening is your lithiums will move from up from the oxide electrode to your graphite electrode, and the reverse will happen on discharge. And I think this Jenga, I mean, I have a sort of naughty jar with one friend. If I say Jenga, I get in trouble, because it seems, quite frankly, the past year I've been obsessed with it. So it's just quite simple just to visualise having the lithium moving one way to the other. And I do know that we haven't got the electrolyte in here and we haven't got the external circuit, but I've got another resource that will explain that. So as well, normally if we were in, say, 101 in Haworth, I would have probably picked on 2 of you to come up with my volunteers. And this is about rate of charge, so we can also think a little, you know, it's going a little bit beyond sort of the curriculum. We're getting students to think, well, also what researchers are actually doing, why, you know, you can't actually use your mobile phone charger to charge, say, for example, your Tesla. You've got to also be careful of rate of charge, because obviously you want to have your device ready for when you want to use it, but also you don't want to compromise safety. So the tower block on the left, you can see we're pulling out the blocks really slow, and that's just a slow charge. But really, we don't want to always charge really slow. But the thing is, if we go mad and go fast charge, and I love this one with the demo, because normally we get students to do it, and they're like, I don't want to make it collapse, but I'm like, let's collapse it, it'd be fantastic. And that is the fast charge. And the final demonstration we do, and this relates to when we normally do the outreach events, we normally get asked, like, I think it's quite nice, we're sort of talking about batteries, you obviously got the chemistry thing, but you've all the chemistry sort of knowledge, but then also the application. So a lot of families at these events say, like, well, my phone's like going really pants after 2 years, what's going on? So you can also visualize degradation. So this is just focusing on the oxide electrode, where we're charging, discharging, and you can just see the whole electrode is getting a bit shanky. It's not staying perfect. And that's how we explain that degradation happens over time. It's like, these are materials in these batteries. And I always think that's quite cool with solid state, especially after working with photovoltaics and solar panels, just how you can visualize, how you can, like, deep down these are materials, but then you see these wide applications. I think it's fantastic. Okay, so this is what I mentioned earlier, that I will go a little bit beyond A level when I just mentioned X-ray diffraction. And this is in the solid states toolbox. So when you're teaching A-level chemistry, I know a lot of hydrogen NMR, carbon NMR comes on to elucidate organic structures. But for us, this is our go-to technique. And what I've showed here, Bragg's law, don't remember this, it just kind of shows you need to have a crystalline sample. And it can tell us what the composition is, the unit cell. You kind of think of the unit cell as just the simplest form of that structure. So you can think, for example, one car in a car park, and if you have the same car relay, the car will be your unit cell. And this is our like go-to thing. So it's got to be crystalline. You can't use things. You can't use glass on here because it's amorphous, where it's like all over the place. The beauty of our materials are they will be crystalline. You know, they're crystalline. They've got a repeating sort of structure. And just to put on, this is a photo of one of our diffractometers. And I think it's just quite nice to see our instruments, sort of X-ray source and detector. So I thought, let's relate back to sort of curriculum again. So I know rock salt, the sodium chloride, is mentioned, and normally I don't think there's a lot mentioned on it. So I thought, let's relate it back to solid state. And you'll see often, I think the bond structure, the stick and bond, or stick and sphere, I think it's called, to the right. Now that's often probably used in the curriculum. I know my old chemistry teacher, Dr. Zane, I think he nicked his model from Aston Uni, but we won't talk about that. I think he's retired now, so it's okay. But you might also see, it's probably more common at degree level, you'll see it visualized in the second, or the one most left structure, where you actually see, instead of having the stick and bond, you'll see it in its polyhedra, the octahedra. And all that is, it's the same where you've got the 6 bonds, but instead it's all meeting up as like a little sort of pyramid, 2 pyramids to make the octahedra. And thing at the bottom, they look really weird, like why is that loads of bars on there? So that is an X-ray diffraction pattern. So when we measure on our diffractometer, that's the data we get out, and then we relay it to make our sort of beautiful structures. So don't worry if this is like, it seems a bit crazy. I've just thought go a bit lower, go a bit further, and hopefully when I talk about the rest, it will make a lot more sense. So, onto batteries. I'm sorry, by the way, I'm very excitable, just because I've been all day, I've been on Zoom, and I thought, well, I just get really excited about solid state. So, and I've got my headphones on, so I apologise if I'm louder or actually accidentally shouting. So, current research efforts, I said I'd mention at the beginning, and I'm going to just touch on 4 different bits. So I'm going to talk about large energy storage applications, high power, recycling, and also what resources you've got available to you if you want to use them. Okay, so large scale grid applications, these are sodium ion materials, and this is where I first started on my PhD. So instead of where I mentioned lithium ion cells, you can actually use sodium. And the beauty of that is the sort of intercalation chemistry. So where say your lithium or sodium is inserting into materials, that's the same. We won't get onto the graphite because you can't use graphite for sodium, annoyingly. So lithium and sodium, I mean, they're different. They are different for different elements, different places of the periodic table. I mean, just below. But they have different physical properties. So you've got different electrochemical potentials against standard hydrogen, and they have different weight. But the thing is, you can use them because of the intercalation. So regardless of sodium being a little bit heavier than lithium, it's a lot more abundant and it's cheaper, which is perfect for lithium. And I will touch on this in the recycle a bit, because lithium, if we start using it, like keep using it to the level we're going to use, it's not going to last for 50 years, and then we've got the same problem. Like, well, we're moving from internal combustion engines for climate change, but then we're going to be using all the lithium, so then what do we do then? So sodium has a sort of answer for if you're looking to still make use of these batteries. So in the large storage applications, for example, you have your battery, so when it's really beautiful and sunny, store that energy in your big battery. And where weight's not an issue, sodium's your guy, or your lady. So I know I mentioned oil rig earlier, and I basically got an excuse to use this video, and it just shows reduction. So I'm going to talk about my sister's work on this bit. It's crazy. There's 2 Driscolls at Birmingham. It's insane. So I just think it's quite nice as well. We teach, you know, at A level, you teach obviously the colour chemistry, and I love colour. Like, with having white samples everywhere, I'm just going to get confused. And I think this is quite beautiful to show how we can reduce vanadium from 5+ down to 4+. Sometimes the green in between might get confused with vanadium 3+, but it's just because you've got the overlap. So this is some of the work my sister has done. So it kind of brings all these ideas together where I mentioned about oil rigs. So I just focus on the reduction of this, but obviously you've got an oxidation happening. They got to come in pairs, but we're looking at the reduction of vanadium. I mentioned crystal structures, and the beauty of solid state is, I just think it's fantastic how we can tune our sort of synthesis methods. And you don't need to like understand this or be like, I know what unit cell that symmetry is. But I think just appreciate when you look at the diffraction data here, you can obviously see they're different, they're not the same. And like the crystal structures I put on, they're different. And I do love Laura's photos of a synthesis of like how different they look. And I think that's also the beauty of like when we do stuff in the lab, it's rather than just having a white powder, I just love, ooh, what have I done? I just remember actually when I was a master's student, I kept thinking someone was leaving the furnace dirty, because I kept seeing like black dirt, and I was like, who's knocking samples over in there? It turns out it was me, and I was just making iodine. But I think it's quite nice to see these sort of physical changes. I'm a big fan of solid state. The next one is about high power applications. So I'm going to talk about lithium ion materials. So I have put brackets anode because I was like, I don't know if I want to use cathode and anode, but hopefully you understand that I'm just relating it back to graphite instead, that side of the electrode. So the issues we've got, instead of just saying, for example, take your smartphone battery and put it into a car, you're going to have issues with graphite, because obviously you want to do the sort of fast charging that I mentioned with the Jenga, but the problem with sort of doing that with graphite, you get something called dendrites, and you can kind of envision dendrites as if you've got your both electrodes. Sorry, that's kind of quite weird. You've got your both electrodes, and what happens when you fast charge is your lithium starts to build, so you get a bridging between the electrodes, and you don't want that, because you're going to have a safety issue because your electrolyte is a flammable material. So big no. So it can't be used for fast charges. And I've got on here capacity. So capacity just refers to, well, how much lithium can we put in, you know, how many electrons can we pull out, sort of thing. So you have different values. So I've mentioned here the lithium titanates and the titanium niobate. So these are sort of different options we can use instead of graphite. And just to sort of, again, you can see the evolution that one structure is not going to be the best that fits all. We've got to develop a solid state chemist. And with using these sort of titanium niobium systems, you're going to avoid the lithium dendrites, which is great. So we've got the safety part of it, which is good. And then we're just working on trying to improve the capacities. And again, I think I'm kind of happy that I did show the sodium chloride structures, so at least you can kind of see, well, how this is. And I've just removed the oxygen because we know the oxygen's there at the end of the octahedron to balance it. But I just think it's quite nice to appreciate that all these different structures are briefly mentioned in the curriculum. There's a little bit more going on. So recycling lithium-ion batteries, so just going to point out this is not my forte, it's my sister's instead, but I thought let's mention them. So you might have heard about the Faraday Institution. So it is a government-funded body to focus on different areas of research for battery technology. So you've got things as low as sort of the synthesis in the labs to then the manufacturing. So it's a whole sort of massive project. And one element of the work packages is the recycling of lithium-ion batteries. So I did mention earlier about lithium sort of reserves, and just to add on to it, you've got lithium and cobalt supply risks. So you can only supply these resources in a certain part of the world. For example, I know you've got district, in Congo, you've got where cobalt comes from, there's ethic problems on the mining. So limited reserves and also ethics and related to related So what else we could do? So we could obviously think about sodium, but you don't want to really put a sodium-ion battery in your car, and or maybe you could, but hey, I'm going to use it for large storage applications. But what else could we consider? And I was doing this practice run through on the bus last night, and he mentioned Cornish lithium to me. And what's really interesting, if you want to mention this to your class, is actually they're thinking about with the mines in Cornwall, might be actually able to use certain minerals there to get our lithium. So that, you know, thinking about all these alternatives, and this is sort of modern sort of news as well, which I think is fantastic. And it just shows that even though lithium-ion batteries born in the 90s, and that's just based on the Sony pattern, there's still a heck of a lot of work to go. And I remember at the missions when I helped out Adrian Wright a few years ago, I remember one parent saying, well, what if my child does chemistry, won't like these sort of problems be done in a few years? Like it seems like research just keeps on developing. There's always some sort of problem going on. I mean, like with Professor Andrew Dudley mentioned how the creation of these polymers has led to like the next sort of issue where actually we've got to fix it. There's maybe looking to recycling, or can we use it, do different things? So science is always evolving. There's always a new challenge, and I think it's just fantastic. You know, just having this sort of interest and delving into these different concepts. So one of the things that we can do, so instead of relying on these lithium reserves in certain parts of the world, is we can recycle. But one of the challenges of recycling is we've got to be safe. And I'm just going to show this video just because I think it's quite good. Hopefully it is at the right place. So one thing with these lithium-ion batteries is you can't just send them straight. I think a lot of them do go to landfill, but as well, I think I've got another video where it's been wrongly processed, or it's accidentally put in the wrong battery recycler, sort of lead acid. And you can just see here, like the panic and Jude trying to put out this battery. And this battery has just gone into farewell runway. And obviously panic. I know students love explosions and that, especially when I was like, in February, I did the top of the bench. And they're always like, oh, wow. But really, in a research lab, you don't want fires. And I always like, you know, we've got to be safe about these things. So as much as the challenges for recycling and having these good intentions, safety's always got to be our highest priority. So you just see smoke filling the camera. So enough of that. So those are just like the sort of different areas of research that are going on at Birmingham. And the final thing I want to touch on is resources. So because I know it was the chemistry teacher's talk, I thought, how can I help you guys out? What have I done that could be useful? And I've mentioned the battery Jenga, so I put links on here to the paper itself. Probably of more interest to you is I've produced worksheets and work booklets for GCSE and A-level. So I went through to the curriculum. I think I mainly looked at AQA. So obviously you've got links to GCSE where it mentions obviously graphite, the graphite structure, but then also the sort of recycling and reuse. So you can tie in sort of the relay project. I have put my answer guides on as well. We got a maker's guide, and there is a more sort of friendly version of the paper. So I put like this sort of booklet together where it's got all the information, all the demos, and I've mentioned the curriculum and sort of things just to watch out that students, when we've worked with them in the past, what they might fall upon, or just sort of things to support you. But if anyone does have any questions or needs support with battery education in future, please just get in touch. I'm more than happy to help. The next resource is, so earlier I mentioned obviously the battery Jenga, it doesn't have the electrolyte, doesn't have the external circuit. So I was that mad person last year who tried to get the group to do this. I obviously couldn't do this in COVID times. So we made a human battery setup of the lithium ion, and it's the same sort of colour setup as the Jenga, but you can see how the lithium ions move from one electrode to the other, passing through the electrolyte. And you can also see these massive beach balls in the external circuit, and it's got the charge and discharge. And we also go a little bit further. We're talking about the solid electrolyte interface, where my boss is dressed up as a security officer because it acts as a protection layer. So it's a bit of fun. It's a different way of visualizing it, because I know not everyone prefers just seeing textbook and these equations, because it does not always make sense. I think I'm quite a visual learner, probably because I'm a little bit lazy when it comes to reading, but hey ho. Some of the resources that have come out of the summer, so I've worked with 2 fantastic students who are undergraduates, and again, it's related to batteries. So I think with these resources that I'm going to mention, rather than it being like core to sort of curriculum, it'll be sort of if they want to do additional reading, this could be for them. So Sophia made these beautiful infographics, and it relates to the sort of manufacturing, how we can do, it's called the next, she was working on the Next Road project. So manufacturing these electrodes, and she uses this analogy of baking a battery or baking a cake, and relates the different sort of types of the battery to just a cake analogy, and she goes from there. It's also got information about environmental impact. And the final thing she did was also create these podcasts. So again, a different medium to whichever sort of learner, or if they want to learn a bit more. So she did about battery education and outreach, cobalt mining, and patent law. So not necessarily things you would associate with chemistry, but I think that's just, again, it's just the beauty of chemistry. Just students probably think, oh no, it doesn't learn about science, but there's so much more where we can just interconnect, and I think it's fantastic. So that's the link there. You can also find her on Twitter. I don't know how many of you are on Twitter, but I love Twitter, thanks to Ruth Patrick, who is knows in the audience. The next student is Emily Hanover. I should mention Andrew. So Sophia was at University of Edinburgh, which we were working with virtually over Zoom. So Emily is a second-year undergraduate at Birmingham, and she worked on adapting the Jenga a little bit further. So instead of I had the lithium cobalt oxide, she did lithium iron phosphate. So you might see battery articles, I think Tesla going for, I think it's Tesla, but saying, oh, we're going to go for safer batteries, and one of the options is lithium iron phosphate. And that's because you probably see from the structure here, if you pull out all of your lithiums, your structure is going to stay standing, you're not going to get a collapse. So it's a different alternative. I don't think the capacity is as well as lithium cobalt oxide, but it's a safer option. And I think a lot of Chinese buses make use of this material. And the other thing is, so she was on the Relay project, so we're looking into recycling. And this, I don't know if you can see my cursor, but the image right at the bottom left. So she made this buzzer game battery pack. So hopefully you might have heard of like the Operation game. And I was like, oh my God, this is a really cool idea. So she made this sort of makeup of what sort of module you'll get in a car. And the idea is you dismantle it without sort of setting off the alarm. And then inside those battery packs, you'd have a smaller module, well, have the cells. And she's done this sort of battery jelly. And that's the image on the right. So we're sort of recycling. It's not as much as like, oh, you know, for example, Andrew mentioned about the plastic and just sorting it. These batteries have a lot going on. You can't simply just take it apart. I think it's time consuming. And there's just lots of different materials. I know some, how sometimes they recycle these batteries is just basically shredding it and you've got a mess. So the idea of the battery jelly is getting students to think about these sort of physical techniques that relate to the recycling industry to get all their raw materials back out. And this kind of back over to you. So we are looking, we need your help basically to prove actually, is this a good idea? We're going to prepare 10 boxes of these sort of recycling packs. And we'd like whoever gets in touch, whether it's with your family or with your class, give these practicals a go and see if there's any use. I've got to mention actually with Emily as well, she has done, like where I've done the worksheets, she's done a whole sort of lesson plan booklet which relates to the recycling part of the GCSE curriculum. She's got a whole presentation of these different things, like a storyboard. So I think I've related it to like Nerdy Mystery, where you pick your sort of routes. Loads of cards, and she's done it for Key Stage 3, GCSE and A-level. So these recycling out box outreach packs would just be to trial these things she's worked on and just see, well, you know, is it of use? Because obviously we've got all these crazy ideas, but if it doesn't actually help the sort of teaching of it, well, we've got to do that. So yeah, if you want to contact me, we are desperate for feedback, and we'll get these boxes sorted. And no, by the way, they will be free. They will be free. Spending Faraday money. And then date for the calendar. So I know you mentioned about CPD. Me and Emily have been talking about this as well. So we're going to set up our own CPD for A-level electrochemistry. We will mention obviously battery because we are battery fans, but we'll talk a little bit more about the reduction potentials, how to work it out, and those sort of things. Oh yeah, I've got in front of me, I've got a recap. Sorry, I'm just looking at like the participants and just gauging the reaction. I forgot to add it, but Mark Reed said to point it out. So mid-October, I will be giving, as part of the emission series, myself and Laura, my sister, will be talking a bit more about batteries, and that will be for students interested in applying for chemistry at degree level. I haven't even planned my presentation yet, but it'll probably be something quite similar. Acknowledgements. So there's a heck of a lot of people I'd like to thank. So it's never just a one-man sort of team, never just, yeah. The science is, I think, it's the collaboration, which is important. So I'd like to thank my boss, he puts in a lot of the Professor Peter Slater, second supervisor Paul Anderson, Emma Kedrick, who is in Matt, obviously Laura, Zoo, Scott, Ruth is here, because Ruth helped me a heck of a lot with the outreach. And I've worked with some amazing undergraduate students, Emily, Sophia, and Emily. I think there's got to be a thing with Emily. So if you name your child Emily, they're probably going to be very successful in chemistry. And the 4-5 and Energy Materials Group. And obviously the School of Chemistry for funding my PhD scholarship. Thanks, guys, for the money. So thank you for your attention. These are my contact details. I'd also like to give a shout out actually to Faraday, introducing the CapMap project, because they now fund me for the outreach stuff as well, which is fab. And yeah, if I stop sharing so I can see everyone's wonderful face, and I'm happy to take any questions. Hopefully, sorry, by the way, I think I overran a lot there. Very sorry.
No worries. Thank you very much, Lizzie. That was excellent. Thank you so much.
I don't know if anyone has any questions. That was excellent, Lizzie. Thank you. I mean, I love the Jenga idea, I must admit. And there's been lots of chats. You haven't been able to look at it on the chat. People really enthusiastic about what you were doing, and Ruth kindly put up some links about where to access some of the things as well. So
amazing. Thank you. And also thank you very much for having me. I know when I first started I was like, oh my god, I'm actually really nervous. So I've been doing a meeting all day and it had like 90 people and I was like, oh yeah, fine. Come in here. I was just like, oh my god. So it's like obviously teachers like know their stuff, and if I you know, if I slip up. But I'd also want to say, like, I hope everyone is doing well during this difficult time. And yeah, if I can support you with these resources, the battery education, let me know. I'm happy to help.
Thank you. Yes, I think everybody's thanking you, so thank you very much. And thank you everyone for coming. It's been lovely to see everybody. You know, this is working, even if it's different from normal. We're actually making contacts, we're finding out things, so it is working well. So thank you, and thank you, Mark, for setting up the Zoom meeting.
It's a pleasure. Great to have our speakers as well. So fantastic, thank you.
Yes, thank you. So, anything you want to say, or otherwise we shall depart.